So to discuss the idea of a limit, we're going to look at how to look at it numerically and graphically. Now, first example that we're going to look at is f of x equals sine x over x. One thing that we need to obviously point out is that we know automatically that x cannot be equal to 0. This function is also in terms of radian, but regardless, you can't have 0 in the denominator. So the first thing we're going to look at is what the graph actually looks like. So in here, I have put in my y equals sine x over x, and we get a graph that looks something like this. So, key thing to keep in mind is that right here, there should be a hole, because you can't have x equal to 0. So in actuality, there seems to be a problem here as we get closer and closer to 0. But it does kind of look continuous otherwise. We're also going to look at what the table looks like. Now this should make sense, because as we go from negative 0.5 all the way up to 0, we are getting closer and closer and closer to what seems like 1, but we have an error when we divide by 0. Also, when we go from the positive side, 0.5, all the way down to 0.1, we also are getting closer and closer to 1, but we are also getting that error. So the idea of a limit is basically as we approach, and in this case we're going to approach 0 to see what the graph is approaching. As we come along here, along the function, it looks like as I come from the left-hand side and as I come from the right-hand side, I am getting closer and closer graphically, and this is the value of 1. I can also see in terms of my table that my numbers are getting closer and closer, coming both ways, to a value of 1. It doesn't actually exist at 1, because if we were actually to look at the graph, it would have a hole there. But we would have an approximate estimation that it looks like it is converging or approaching the value of 1 as x approaches 0. Now this is referred to as a limit. And how we write this with proper notation, what it means is that we have a limit as x is approaching my 0, so for my x terms is getting closer and closer to 0 for the function, and it's going to end up having a 1 value for your y, or for your function. So the formal definition for the limit, we're not going to use the epsilon delta proof. We're just going to talk about it in terms of the general definition of a limit, is that if f of x is defined for all x in an open interval containing that value of c. So in this case, our c value was 0. It contains 0 in terms of my x values within the region that I was looking at in this graph or in the table. But it does not necessarily exist at c itself. So it's not actually defined for that value of c. We have a hole there. Then the limit of the function as x approaches c is equal to L. In this case, L is my 1 value. In this last example, this was going to be 0. This worked out to be my y value of 1, and my function was sine x over x. There's a theorem that basically makes sense if you think of it graphically. If you have two constants c and k, and as we're approaching, again in terms of my x value, for a function that's defined just to be a constant. Now a constant function works out to be a horizontal line. So if I'm approaching any value c from the left-hand side and from the right-hand side, if I have a constant function, this value here is going to be just equal to k. So the left-hand side is approaching k in terms of my y value, and the right-hand side is approaching my k. So it's kind of a straightforward theorem for that one, but that's basically what it represents. The next part of this theorem also says that if you again are approaching some value c for the function x. Now again, thinking back to what the function of x is, it is a line with a slope of 1, goes through the origin, like so. So if I'm approaching any c value, because the slope is 1, if I'm approaching it from the left-hand side or the right-hand side, I will be approaching the c value. And it doesn't matter where I am on the graph. Negative c is going to relate to negative c. So whichever value I wanted to plug in for my c value, is on the negative side, positive side, just a different constant value, is still going to approach the value that is here. A couple other definitions we need to know about is like one-sided limits and infinite limits. One-sided limits basically say that, let's say if we were looking at a graph and we were wondering if the actual limit exists. Well, we can look at the left-hand limit and the right-hand limit. Now where this will come in handy is when we have one that actually doesn't have a limit at that particular point. My left-hand limit as I approach C will be coming from the left-hand side. What am I approaching as I get closer and closer to C? Well, let's call that point A. So in this particular case, the left-hand limit coming from the left-hand side, approaching C, we get an A value. Whereas a right-hand limit coming from the positive side towards C, we're going to get whatever this value is down here at B. Now the limit actually exists if both of the one-side limits exist and are equivalent. In this case, the left-hand limit and the right-hand limit are not equivalent, so therefore the overarching limit as you approach C does not exist. But we can write it down as a left-hand limit and a right-hand limit. So in this particular case, for this particular function, as x approaches C from the left-hand limit for this function is going to approach A, and here the limit as x approaches C from the right-hand side is going to equal B. Overarching, the limit, if I was just to say as x approaches C of your function, does not exist because they're not equivalent. Now infinite limits is another one that's quite interesting. It's basically, well, first of all, infinity is not an actual number. When we talk about limits, they're actually defined limits. So when we say an infinite limit, we are generalizing that it's approaching an extraordinarily high number or an extraordinarily low number. And again, it's conceptual, so technically the limit doesn't exist, but we can write it in terms of infinity or negative infinity. The cases where this is going to occur really is going to be whenever we have an asymptote. And let's say C was our asymptote. Now, again, you want to consider the functions and say as you're approaching C, the left-hand limit and the right-hand limit have to be approaching the same value. Now if you notice here, C is an asymptote. This one's going to shoot up to infinity, this one's going to shoot up to infinity. So for this particular case, because the left-hand side and the right-hand side are both approaching infinity, we can say that the limit is approaching infinity at C. Whereas, if I had something like this, and we had an asymptote, and this one decides to go down this way, and this one goes up this way, we'd have a left-hand limit that goes to negative infinity, a right-hand limit that goes to positive infinity, but the overarching limit as I approach my C value in this case is undefined because they're not going to the same location. Now one interesting instance is if we were to have a graph like this. What if we have a hole in our graph, like so, and it does something over there, and it has a point. That's C. What is the limit going to be as you approach the C value? There is a point that's associated at C. Is this the limit? Or is this the limit? So I want you to consider what was said in this video and come to class ready to discuss what that could possibly be.